Flexures are used in a wide variety of application areas such as precision stages, precision surgery, aerospace mechanisms, deployable mechanisms, optical precision equipment, and consumer lifestyle products. The function of a flexure is to allow motion in some directions while supporting other directions. Several flexure elements can be combined to create, for example, a hinge that allows only one rotational motion. In turn, several of these flexible hinges constitute a mechanism, in this case with 2 degrees of freedom. Flexure joints have some principal advantages over their traditional counterparts. The lack of play and friction results in predictable behavior essential for precision positioning. Flexure joints are also virtually maintenance and contamination free. However, existing flexure joints suffer from a major drawback. At large deflections, the support stiffness decreases strongly. Therefore, flexure-based mechanisms become relatively large. To overcome these drawbacks, a disruptive design approach is being developed at the Precision Engineering Lab at the University of Twente. The approach encompasses 5 main ingredients. Flexures are assembled in parallel to reach the required degrees of freedom. In this case, the torsional degree of freedom of the initial leaf spring is constrained by a folded leaf spring in parallel. However, at large deflections, the parallel approach is insufficient. An external force then still leads to a large unwanted torsion component in the leaf spring. Additional flexures in series are added to minimize decrease of support stiffness. In this case, the torsion component in the leaf spring is strongly mitigated by rerouting it to support directions. The combination of a parallel and series topology results in a hybrid topology. Unwanted forces in compliant directions are rerouted to support directions even at large deflections. Basic building blocks with properties for large range of motion are defined. Different layouts are generated by combining several of these smart building blocks. For a given layout, an optimization method is used to find the optimal shape. By iteratively interchanging the building blocks and optimizing the shape, an optimal topology can be found for a flexure joint. This way, the performance of thousands of possible topologies are evaluated in an optimization algorithm. These complex flexure topologies can be analyzed with readily available finite element analysis code with high accuracy. This comes at the cost of being very time-consuming. To decrease the computational time needed to analyze thousands of topologies, efficient modeling is crucial. The Spacer multibody method combines invariants for rigid body motions with linear beam models. Consequently, this method is several orders of magnitude faster while capturing the relevant geometrically nonlinear behavior. The smart building blocks are modeled with closed-form analytic equations to describe their nonlinear behavior in a very efficient way. This method minimizes the number of required spacer elements and helps the iterative procedure in finding the solution even faster. An efficient collision detection scheme maximizes the volumetric usage of the flexures, even in deflected positions. The performance of the optimal design is corroborated using a common finite element analysis package. To enable complex topologies at low cost, additive manufacturing technologies are being utilized. Materials include plastics such as nylon and ABS, as well as metals such as titanium. The presented flexure topology synthesis will result in a new class of flexure joints, impacting mechanism design by becoming keystone elements just like roller bearings are today. Not only will precision mechanisms become much smaller with increased performance, new applications that were not feasible or even possible before, such as robotics and prosthetics, are now within reach.